Okay, welcome everybody to lecture 15 of CSE 548, the analysis of algorithms. Let's see, let's start off first of all, are there any questions about any issues that maybe concerning the program? Let's start off with the programming project. How many people have working programs that do something, at least generate some correct answer? Okay. We've got, okay, some people backed off when I asked for a correct answer, okay. But, so we've got about half the people seem to sort of have programs. How many people haven't started it yet? Okay, a few people, okay. I urge you to get in there. If you're not very good at this, okay, you're not very good at programming, make sure you do something simple to get going. The real simplest version of the program, which simply goes through all permutations and for every permutation counts the length of the edge you generate, should be relatively simple to write. If necessary, look at some books in the library on backtracking. Okay, there are books, almost any book entitled Data Structures will have a section on backtracking. Okay, many books on algorithms, unfortunately ours doesn't, has a section on backtracking. If you're really confused, you don't understand how to generate the permutations, either talk to me or go to one of those books. Okay, make sure that you get the help that you need. Okay, let's see what's the fastest, how fast people's programs are. How many programs are capable of doing up to 10 vertices comfortably? Okay, raise your hand proud if you've got up to 10 or more. Okay, got a bunch of people. Okay, how many people getting up to 20 or more? Okay, we got some people, still got about 4 or 5 contenders. How many people are up to 25 or more comfortably? Okay, we've got 1 or 2 hand waving. Okay, and the largest I've heard is still on the order of 30 to 40 vertices. Okay, in fact, I received a demand for a larger test files. Okay, which I'll try to set up. Okay, but again, don't worry about that if you haven't started it. If you haven't, make sure you get something working first. Okay, but once you get going, I urge you to spend some time thinking about pruning. Okay, trying to think of how you can eliminate certain permutations from consideration. And if there's any questions about that, I'll answer them now. Question? No, the question is, do you have to print all the answers to the problem? And the answer to that is no. What I mean by all the answers. Any one problem may have lots of permutations that realize a particular bandwidth. Okay, you do not want to print all of them. You do not want to generate all of them. Okay, you want to only print one representative solution. Okay, now why is that? Let's think about it. And this is actually an important issue in pruning them. Okay, suppose I ask you for all the solutions to the complete graph, okay, where the complete graph, remember, is the case where you've got every vertex is connected to every other vertex, like a star here with these extra edges. Any way you lay it out, there's going to have to be an edge between the leftmost and rightmost vertex, correct? So any one of the n factorial layouts for this program is going to be exactly the same. So if you're telling me you want to solve the complete graph and print out all solutions, you can't hope to do it for more than n equals 10, okay, or so. Okay? What the right thing to do is to say, as soon as you can convince yourself there's no better solution than one which stretches from left to right, you want to say, no more, I don't need to look at anything more. So in fact, the essence of pruning is to not generate a lot of solutions of the same size, is to make sure that you don't generate any solutions that are that size, okay? That you eliminate anything that's going to be at least that big, okay? And changing from bigger to at least that big is going to probably lead to a lot more pruning, okay? So by all means, I only want one solution of any size, okay? Because, and there's lots and lots of different solutions. So if anybody's program spits out the same solutions as the answers I've posted, I know something suspicious, okay, because most of the time there's lots of different solutions for doing that, okay. They all have the same bandwidth, okay, but there's lots of different permutations that generate that, okay, and so trying to figure out the best way to, so however you do the pruning, presumably in most graphs, quite often you're going to end up with different solutions of the same bandwidth. If you end up with different bandwidths, then either your program or my program is wrong, okay, and my money's on your program, okay. But I can be convinced. You can convince me very easily once you show me a better solution. Okay? Any questions? Okay, question.
How good is your program?
How good is my program? Well, actually, I'll have to confess, my program is sort of a solution from the past. Okay, and my program's capable of doing about 30 vertices. Okay, but this was written by an undergraduate. Okay, last time I taught the course for undergraduates. Okay, so I expect, of course, better solutions now that we got a bigger crowd. But we'll see. We'll see. We'll see how well we can do. Question?
What is the fastest algorithm you've seen so far?
Fastest. We're talking about fastest. There's difference between fastest algorithm and fastest program. Fastest program, like I said, I've heard rumors of solutions that are capable of going up to 35 or possibly up to 40 on certain instances. But presumably the program's dying. You know, we'll see. Okay, that's why do the best you can, do as much pruning as you can, and we'll collect and we'll get official results after people turn them in. Okay, you know, for see who's actually fastest and whatnot. And again, there's separate grading for the grads and the undergrads, so don't be discouraged if your program can only get up to 20 or so. Okay, or even 15 perhaps. Okay, any questions? Okay, so again, realize that there's a couple different tricks people have been using to speed things up. One idea that some people have noticed is that if you start from a good solution, okay, if you start from a permutation that's good, maybe you get more cutoffs. Since let's say you're eliminating anything that's bad, once you know a good solution, a lot of things are going to look bad relative to that. So some people have been investing some time in trying to, sort of identify good solutions beforehand. Okay, that may or may not be a win. Okay, other people have been trying to do very carefully. Think of good pruning characteristics. When do you know you can eliminate such things? Okay, and that's something to think about. You can, if you're clever about how you do your search, the possibilities for pruning are large. That's why the programs are getting faster. Okay, is because some people are doing good pruning. Okay, there's some opportunities for using symmetry detection. Okay, and think about that. Okay, any questions about that? Okay, final thing is that I'd urge people, when you're just about finished, when you're just about ready to say, I've done as much searching, pruning as I can, I urge you to go use a profiler. Okay, this profiler program on the system, typically called prof or gprof. Okay, just to give you some idea of where your program's spending the time. Okay, because I think that when you start looking at your program through that, it'll be an educational experience to use a profiler. And since in your real life you may have to tune programs and make them faster, it's good to know that there are such tools and how they work. Okay, and so I urge you to play around with that. Okay, that said, keep going, and we look forward to the results. Okay, coming in next class. Okay, any other questions about the program? Some other issues. First of all, there's Pizza with the Prof on Monday. Still a couple sign-up sheets on my door. If you're interested, sign up. Last class, I passed out a survey for students, and I read through the result. There's some interesting things I learned. A couple issues that came up. One thing is a lot of people think I'm going too fast. I'll try to keep that in mind, maybe slow down a little bit. Okay, although today we're going to change topics to a topic that I think might be a little bit more accessible than some of the dynamic programming stuff. There are some questions about how picky we were on the grading. We'll try to be better about that next class, on the next midterm. And there were some people who still have problems, who are complaining that they can't get access to the web pages, okay, and that was sort of a serious problem. If you really haven't figured that out, there's got to be a way we can do this with university resources. Maybe the computing center can get you an account or something like that. If you're really bothered by the fact that you can't get access to the web pages, come to me and we'll see if we can figure out a way to do that. Okay, anything else? Final sort of pre-issue is projects. The graduate project proposals are due sort of today. Okay, I'm not grading the project proposals. Okay, what I want to make sure is that everybody is mated with a project that they're happy with. Okay, so the purpose of this is to make sure if you have an idea for a project, come to me to talk about it. Make sure that you've got an idea that you're sure that you think is going to make for a good project. The worst thing is going to be if 2 days before the projects are due, suddenly you look at the project proposal you wrote up in 30 seconds by copying out one of my problems from the list, and suddenly realize you don't know what it's about, or you don't know what to do next. Okay? That's why I urge you to start thinking about it. Make sure you have a problem to work on. Okay, that's the purpose of the proposals. And I want to make sure everybody's mated with a problem. Any questions about the grad projects? Very good. Okay, what I'd like to do is to talk about a switch gears a little bit from dynamic programming into graphs. We'll actually see dynamic programming again when we start talking about shortest path algorithms. Okay, so it's not going away. And if you haven't caught on, I urge you to think about it. Okay, but what we're going to be talking now are going to be graph algorithms, which I think is really one of the more useful areas in computing. Okay, and the reason why graph algorithms are useful is because graph problems really come up in all kinds of different applications. Even applications where it's not obvious at first that it's a graph problem. Okay? In fact, if you ask me what the single most important thing to know about in graph algorithms in practice, it's actually not so much the details of algorithms. It's not as important, I think, to know, let's say, how exactly the minimum spanning tree algorithms work, although we'll go through that. The real key, the real payoff, if you know about graph algorithms, is to know what the basic problems are and know that you can compute it once you know the name of what your problem is. A lot of times when you have a problem that comes up in practice, you know it has something to do with graphs, okay? But you don't know quite what it is. And the ability to take your problem and model it as a graph problem is the single most useful thing you can do, okay? Because once you've got a graph problem, you've got a name, and then you can look in the book up what to do. Okay? So it's really important to understand problems and understand how to model things in terms of the graphs. So what is a graph as far as we're concerned? A graph is going to be, it's something that consists of a set of vertices, okay, and a set of edges, where each edge is a pair of vertices. Okay? And the reason why graphs are important is because any binary relation, okay, can be modeled as a graph. A binary relation is simply a set of pairs of elements. Okay, like for example, you may have a bunch of people, and you can have a pair of elements if one guy is related to the other in some way. Maybe they're friends, maybe something like that. Okay, and what graphs are important is because you can represent any relation. So what's an example? One example is we can consider a network of roads, okay, where you've got a set of cities. Let's zoom in on my graph a little bit. You've got a set of cities, Stony Brook, Riverhead, Shelter Island, and stuff like that. Certain pairs of cities are connected by roads, okay? There's no direct link from Greenport to Sag Harbor because there's water between them, okay? But we can if we go through the intermediate point of Shelter Island. So if we want, we can model the network of roads, okay, by each vertex corresponds to a city or a junction between roads, and there's going to be an edge defined if the two roads, if they're between any two cities, there is a direct link between them. Okay? So in fact, we can represent every road network by simply a graph. Okay? And so if you want to know, for example, can you drive between Montauk Point and Orient Point, that problem is now well defined as a graph problem. You want to know, is there a path in the graph that goes between them? Okay? So any network of roads can be represented as a graph. Okay? Maybe you'd like some additional information on your graph, like you may want to know for each road how long that road is. Okay? So sometimes we'll be talking about so-called weighted graphs, where every edge has a weight with it. Okay? But basically, a road network is a graph. Similarly, an electronic circuit is modeled as a graph. Why is that? Again, typically the junction points, okay? Like here's a junction point, there's a junction point, there's a junction point, there's a junction point. The junction points would correspond to vertices in the graph, okay? And the components would correspond to edges, okay? We have an edge between, if there's two junctions that are spanned by a component, we'll put an edge there, okay? And if that component is just a wire, we have a short circuit between 2 points, okay? But so in a lot of problems, when you simulate circuits, the way to think about them is in terms of graphs, okay? And in a lot of different problems, the basic idea is to take your problem and model it as a graph, and then ask yourself, how does what you want to do correspond to a well-defined graph parameter? That's the big issue in using graph algorithms. Any questions so far? Okay. Let's look at a more concrete example of a graph and think about where where some of these sort of graph terminology comes in, so we can sort of practice modeling things in terms of graphs. So what I'm going to talk about is a graph that we're all familiar with, although maybe we've never thought of it as a graph. Okay, is let's model the situation of friends. What are friends? Friends are two people who know each other. Okay? My claim is that the idea of friendship in the world, okay, or in the classroom or in Stony Brook, can be thought of and understood basically by defining a graph. What's the graph? Well, the vertices of our graph are going to be people. Okay? And we're going to have an edge between two people if and only if they're friends. Okay? So if we live in a happy world where everybody knows everybody, what is the graph going to look like? Okay? It's a complete graph. This would be a happy world where everybody is connected to everybody else. What does an unhappy world look like where there's no friends? Okay? Then you've got, this is the unhappy world, okay, where nobody has any friends, so there's no connection whatsoever between friends. Okay? In general, we can think about modeling for any group of people a friendship relation. Like here's some relation I have. You know, back then, Ronald Reagan had a lot of friends. Okay, Saddam Hussein had no friends. Okay, so that's the difference here. Okay, and George Bush didn't have very many friends, which is why he didn't get reelected, I guess. Okay, so my claim is that for any set of people, we can define the friendship graph. Okay, of what the adjacencies are. Now, sure, we can define it, but what good is it? And the point is that now once we have a graph, a lot of questions we might want to ask about friendship or relations sort of can be directly mapped to graph theory terminology. And so if you want to solve problems, conceptually what you do is you say, here's my graph, what's the problem I want to solve, is there an algorithm for that problem? That's how you solve a lot of different things. So what kind of issues can there be about the friendship graph? First of all, there's an issue. If I'm your friend, does that mean that you're my friend? This is a deep question, okay, in real life. Okay? The issue, if you have the friendship graph, you can resolve that question by looking at the graph and telling whether or not it's directed. We say that there's two different kinds of graphs. There's directed graphs and undirected graphs. Okay? In an undirected graph, we have an edge, x, y. Remember, each edge has a pair of vertices. If it's undirected, if x being a friend of y implies that y is a friend of x. Okay? So if it's undirected, if edge xy implies edge yx is there. A graph is directed if that's not necessarily true. Okay? So for the friendship graph, maybe that's not so clear. But let's look at some other graphs. Suppose we talk about the heard of graph. Okay? Namely, we have a set of people in the world, and there's going to be an edge from me to every person who I've heard of. Okay? Is that a directed graph or an undirected graph? Okay? If I've heard of you, does that mean you've heard of me? Okay? The answer is no. I've heard of Sylvester Stallone. Sylvester Stallone has not heard of me. Okay? The heard of graph is an undirected graph. Okay? Is a directed graph. Okay? Suppose we consider the had sex with graph. Okay? If I have sex with someone, presumably they're having sex with me. Okay? Unless there's things I don't know about. Okay? Thus, if we consider that degree of relation, okay, that would correspond to an undirected graph. Because the relationships, by definition, always go both ways. Certain graph problems work very well on are designed to work on directed graphs. Certain graph problems have meaning on undirected graphs. Some are for directed, some are for undirected. Okay? And it's important to realize conceptually when you have a problem whether the graph is going to be directed or undirected. If you can't figure that out, you really don't understand your application. Okay? And sometimes the issue is somewhat subtle. Okay? But it's important to sort of make sure you get that clear and make sure the answers you get back are that. Okay, any questions about friendship or direction? Very good. A second question we might ask about friendship is, am I my own friend? Okay? And again, this is a philosophical kind of an issue. If you were your own friend, how would that be modeled in the friendship graph? So if we go back to Saddam, suppose Saddam's his own friend. What does that mean? That means we've got an edge basically going from him to himself. Okay? We call an edge like that to be a loop, which makes sense if you look at how it's drawn. Okay? When we have a graph algorithm, okay, or a graph problem, one of the first things we want to ask about our graph is, does the graph have any loops in it? Okay? Loops sometimes mess things up. Okay? Certain graph algorithms will assume that graph does not have a loop in it. Okay? Usually the loop is not that hard to deal with once we sort of, like for a lot of different problems, the loop doesn't really matter very much. But sometimes if we don't deal with it correctly, we would get incorrect results in our, what it means. Okay? Like for example, if we ask ourselves, does Saddam have a friend? Usually we would not, it would mess things up if we sort of permit him to be his own friend. Okay? That's not clear that that's what we mean. So we have to ask ourselves whether the graph has loops. Likewise, there's another question of whether or not you can be somebody's friend more than once. Okay? Like for example, maybe Ronald Reagan and Nancy Reagan were really good friends. So we might want to have more than one edge. We call a graph a multigraph. Okay? Okay? If it has multi-edges, namely meaning there's more than one edge between a pair of nodes. Okay? And again, in certain applications, multigraphs make sense. Can anyone come up with a situation where it does make sense to have multiple edges between a given pair of nodes? Okay? Okay, intercommunication lines would be one idea, okay, because you might want to have some redundancy. There might be two different wires between two houses. Or the other suggestion was in electric circuits. Okay, we could imagine a parallel electronic circuit. I don't know if I had it here, okay, but actually, yes, I sort of did. Here, you could imagine in this circuit, there is a multigraph, because here is basically my vertex. My vertex is this junction corresponding to all of these things. Okay, and my vertex is this junction. So there's two different edges corresponding to two parallel paths in that graph. Correct? There's an edge from here to here for that resistor and here to here for that capacitor. So it's certainly true that circuits, for example, are modeled as multigraphs. Okay? So you can have multiple, so really there's sort of a difference here. You can have multiple edges and they can mean different things, okay, as in the case of the circuits, okay? And so sometimes you're going to want to store the graph with multiple edges. Sometimes if you have multiple edges that do basically the same thing, maybe you might just keep count of the number of copies of each edge. But here's a good example of the fact that the edges can be different and sometimes have to be dealt with as a multigraph. Okay? Any questions? For the friendship graph, it doesn't make much sense, I think, to talk about multigraphs. Okay. Another question we might want to ask about the friendship graph, okay, is there some link between two people? Okay? Do I know somebody that knows somebody that knows somebody that knows Bill Clinton? Okay? Would be a kind of question you would ask. If you've seen the play 6 Degrees of Separation, or you've heard that phrase, okay? That's really the question of saying, is there a path between two people in the friendship graph? Okay? So a path, in a graph theory sense, is a sequence of edges such that they connect vertices. Okay? Two different vertices. Okay? And in real life, Mel Brooks is my father's sister's husband's cousin. So if we take a look at the friendship graph, there's a portion of the friendship graph in the world which has me on one side and cousin Mel on the other. Okay? And there's a path here of length 4 edges, okay, between my father, my aunt, and my uncle. Okay? So that's what paths are in graphs. Okay? Any questions? Okay? Yes, this is true. Cousin Mel. I've never met Cousin Mel, but that's true. Who's Mel Brooks? Okay, that's sad. You hurt my cousin. Okay. My cousin, he made a lot of funny movies a while ago, and now he makes some movies that aren't quite as funny. Okay. Okay. But anyway, but when we think about paths in graphs, one thing that we should realize is that there's often more than one path in a graph. Okay? For example, there's lots of different ways that you could get in the friendship graph from me to Uncle Lenny. Okay? From me to cousin Mel. Why? Well, my mother certainly knows me, and my mother certainly knows my father. Okay? So there is a longer path, okay, in this graph. One thing to realize about paths in graphs is there's lots of them. If you have if your graph has a lot of edges in it, okay, or it's a possibility of a lot of edges in a graph. It's possible there's an exponential number of paths between two nodes, okay? And one issue that we may want to know is how close is your link, okay? If I'm trying to impress you, okay, with my clout with cousin Mel, okay, the wrong thing would be to say that he's my mother's husband's, sister's husband's cousin. The right thing is I'd be interested in the shortest path between two nodes. It'd be nice if it said it was, sure, that's Uncle Lenny's cousin, okay? And now I've got a link of only two edges. So when we talk about these graphs, there's often lots of paths, and in a lot of applications, what we're going to be really interested in is the shortest path, okay? Not just geographic interest. It certainly makes sense when you want to find the shortest way to drive between here and Riverhead, that you want the shortest path in some graph. But shortest path problems come up in lots of different guises. And I think this question of trying to impress somebody with a link, okay, is an example of such a thing. Okay? Any questions about that? Okay, that's really the shortest path. Okay? Another question we might ask ourselves is it true that there is a path of friends between any two people? Are we really one world? Okay, in the sense that if you wanted to, that there is indeed between any two people a link, some kind of path of getting them in the friendship graph. Okay? If so, what we're really asking in graph theory terms is whether or not the friendship graph is connected. Okay? We say that a graph is connected if between any pair of vertices there is at least one path. Okay, here we've got a connected graph. Okay? A graph we say is connected if between every pair of vertices, okay, there is a path between them. Okay? And testing whether a graph is connected or not connected is an important issue. Okay? For example, in the bandwidth problem, okay, some of you may have noticed something. Suppose I give you a disconnected graph. Okay? A graph where there is not, the graph is actually in two pieces. What is a good issue? What is a good way to reduce the bandwidth of such a graph? Or what is something we need to know about the layout of such graphs? Okay? Suppose this was vertex 1, 2, 3, 4, 5, 6, 7, 8, 9. One thing we'll notice is if they're separate components, we might as well put all the vertices from one component together before we have any vertices of the other component. Because there's going to be edges going between components and edges going between components, but within components, but never an edge across components. So if there were disconnected graphs in that data set, which there may well be, okay, I don't make any promises, one thing that would seem like a good idea is to make sure that you break it into components, connected components first, okay, and then solve the bandwidth problem on each component. It's a smaller job, okay, should run faster, okay, and it's going to be good. So the question of whether a graph is connected turns out to be useful for lots of different reasons. Okay? Obviously, if you're building a highway system, you want that highway system to be connected. Why? Because if it's not connected, that means that there's two places in the country you can't drive between. Okay? Which is generally a bad idea. Okay? Any questions about connectivity? Now, one thing that's interesting is issues of connectivity are quite different on directed and undirected graphs. Okay? So let's think about something. Suppose we had a road network where there were one-way streets. Okay? And there's an edge from here to here, an edge from here to here, and an edge from here to here. Is this graph connected? Okay? Okay? The answer is no, or depends upon what you... The answer really, I would say, is it depends what you mean by connected. Okay? If you want to say, is there a path, is there asphalt between any pair of places, the answer is yes. Okay? But in fact, if you want to say, can you drive between any pair of places, if these are one-way streets, the answer is no. Because you could drive from here to here, but then you got to sell your car, because there's no way you can get from here to any place else without violating the signs. Okay? So the issue of connectivity of a graph, again, we'll go through this a little bit more later. We'll actually look at algorithms for connectivity. Okay? But it's important to see that there's a difference between connected graphs and connected, what we call strongly connected graphs. We say that a graph is strongly connected if there is a directed path between every pair of vertices. So if we go back to this runway street, if we add a road from here back to our starting place, we can get from here to here, we can get from here to there, we can get from here to there, we can get from there to here, and from here get back to every place else. So it's possible to make the graph strongly connected. Okay? Any questions about that? Another question that comes up a lot when you're talking about people is who has the most friends? Okay, or how many friends do you have? Okay? In graph theory terms, if we're talking about the friendship graph, what is the quantity that would relate how many friends you have? How would you measure how many friends you have? Yeah. The degree of the vertex, or how many edges are adjacent to you. Okay? So we say that the degree of a vertex is the number of edges adjacent to it. Namely, the number of edges going out of a particular vertex is its degree. Okay? So if you're an isolated vertex, if you're Saddam Hussein, what's your degree? 0. If you're living in a world where everybody has friends, if you've got n degrees, n vertices, what's the degree of everybody? n minus 1, because it's n minus 1 if the graph is not a multigraph, does not have a loop in it. Okay? Yes?
What if Saddam Hussein has a loop? What degree?
Okay, this is what you're getting at is an interesting question. Okay, what is the degree of this vertex? Well, to a certain extent, it depends upon what you wanted to, how you want to define things. Okay? So, for example, if you add a self-loop to a vertex, so you have one edge with a loop in it. Okay? How many edges are adjacent to that thing? I would probably say 1. Okay? Because, in fact, the fact that you've got two sides of it doesn't really mean anything. It's one edge. So usually I'd say a loop would count as one edge. But realize that it depends upon your application. Okay? So I mean, sometimes degree. One thing that's interesting about graph theory terminology is that it gets hard to define it. The definitions change slightly when you allow multiple edges, when you allow self-loops. And so you've got to be conscious of the fact. You've got to, sometimes when we make an assumption, we're usually dealing with simple graphs, meaning no self-loops and no multiple edges. If so, the degree is well defined. If not, then you've got to probably come up with a slightly different definition of degree tuned to your application. Okay? What makes sense depends upon your application. Okay? It's not sort of a loyalty oath type of thing. Okay? It's like, in this case, the degree would depend upon how you want to count friends. Okay? And my guess is you'd probably want to count Saddam as having one friend if he has a friend, if he's his own friend. You don't want to give him credit for 2 friends. Okay? But that's up to you. Okay? Any questions? Okay? Another question that happens, certainly in high school, when you're talking about friends, is what's the largest clique in the high school? Okay? Again, some of you did not go to American high schools. Okay? But well, maybe some of you didn't go to the high school that I went to. In the high school I went to, there was always a social concern about this group of people who sort of hung out together. Okay? They all knew each other and they sort of stood off by themselves. Okay? What you might want to say is sort of, how do you define a group of people in a, let's say, a group of people, all of whom know each other? Okay? We say that a social clique, okay, I think in general would be defined as a group of mutual friends, all of whom hang around with each other. Okay? So if we have a social clique, Let's say these 5 people are in a social clique. What would their friendship relationships between each other look like? Okay, it'd be a graph, but what kind of graph? Complete graph. Okay, sorry. Now, it may be possible one of them is not snotty enough that they'll talk to somebody else. Okay? So we could have a graph like this. Often when we have a graph problem, we might ask ourselves, what's the largest sort of big group we have in the graph? For example, let's say you wanted to find what is the biggest club on campus. What you're really asking, I think, is what is the largest complete subgraph, okay, in the graph? And that is something we call a clique. Okay? I'm used to pronouncing the math term as clique, okay, and the social term as clique, but I won't defend that. So one thing that you want to do with a graph often is find large, dense subgraphs, okay, of people who all know each other, or things that are all related to each other, okay? Like, for example, a friend of mine is working for the IRS, okay, the tax people, writing a program to try to detect tax cheating, okay? Now, one of the things that happens in tax cheating is that there's people lying on their returns, which is one issue. There's also people who sit down and write out hundreds of phony returns, okay, in the hopes that they will get a refund check and then run with it, okay, before they do anything. So there's a big problem at the IRS in trying to detect returns that are similar. So what do? They build a graph where every vertex is a tax return, okay, and they add an edge if 2 tax returns look suspiciously similar, okay? So just because my tax return looks similar to yours, well, maybe we earn the same amount of money and things like that. But on the other hand, if I see a bunch of tax returns, all of which are mutually close to each other, okay, I'm looking for a large clique in that graph. And that's what they do, okay? So the idea of looking for a large thing, densely connected thing, is a clique. And that's an important thing to think about when modeling problems, is graphs. Okay, any questions about that? Or why you should only write 1 tax return per person? Okay, that's another issue. Okay? Another issue in the friendship, okay, is sometimes you spread gossip. Okay? You tell a story about somebody. Okay? And it's such a good story, you'll spread it to all your friends, and they'll spread it to all their friends. One question you might ask is, how long will it take for that gossip to get back to me? Okay? That, I say something juicy about somebody. And how long is it until somebody tells me the story back? Okay? In graph theory terms, what would that be? Okay? What would we need in order for me to hear my gossip back? Okay? You need some kind of a cycle. If I tell you and you tell somebody else, then it doesn't get closer to me. But if this guy remembers to call me, now I've heard the word back. Okay? So the time till I hear the rumor back, okay, the gossip length, is going to depend upon the length of the shortest cycle in the graph. Okay? And so one thing that's often important in modeling graphs is thinking about them as cycles. Okay? Or trying to identify cycles in the graph. If there's no cycles in the graph has a very simple structure, and there's things that we can do with it, knowing that. Okay? But in a lot of cases where there are cycles, we're interested in maybe the shortest cycle or maybe the longest cycle. Okay? The shortest cycle defines something we call the girth, and the longest cycle is called the Hamiltonian cycle. Okay? These names by themselves, the girth is not so important. Hamiltonian cycle you'll probably hear a lot. Okay? But the important thing is to realize that there's times when the problem you want to know the answer to is modeled by a cycle in the graph. Okay? Question? A simple cycle, okay, is, suppose, let's say that let's say that Saddam is his own friend. Remember that. Okay? How long does it take when Saddam tells gossip about somebody for it to get back to him? Okay, you could say 0 time, or you could say 1 unit of time. So it's sort of the multi-loop thing, again, causes trouble in interpreting that. But more than that, suppose, let's say we don't want to know the shortest cycle, but the longest cycle. Okay? Suppose I have a graph that looks like this. Okay, so it's got these 4 vertices. What's the length of the shortest cycle, of the longest cycle in that graph? Okay, 1, 2, 3, 4. Sorry if you can't see it. What's the length of the longest cycle in this graph? Okay, so you say 4 vertices. Why isn't the length of the cycle 6? 1, 2, 3, 4, 5, 6. Or 7, or 9, or 12. So it's a question not of whether the graph is simple. The graph itself was simple. But the question is whether the cycle we're talking about is simple. Okay, so there's a difference between whether we talk about the longest simple cycle, okay, where we say a cycle is simple if no vertex repeats. Okay? Except the first and last ones, right. Okay? Question?
Are we going to be discussing about the concept of weight of edge?
Okay, later on there's also a question of what if the graphs have edges have weight? Like, for example, let's say we consider the gossip problem. Let's say that it takes a certain amount of time for people to talk to each other. Okay? So let's say that I have a graph that looks like this. Okay? Where, again, I've got these vertices. I now spread a rumor. It takes 1 unit of time for me to tell this guy. This guy has 2 other friends, one of whom he likes a lot, so he talks to him. One of whom he doesn't like. So it takes 100 days till he talks to that person. Might take 10 units of time for this person to call that and 1 unit there. The shortest cycle in the number of edges is this one, 3. But the shortest cycle in terms of length is going to be, in fact, have more edges. So there's going to be different issues between whether we talk about a weighted graph, where the edges have numbers, okay, or an unweighted graph where they don't. Okay? And it's important when you have a graph problem to try to break things down, to look at your applications, know what you're doing, know what the names of things are. Okay? If you know what the names are, you can look them up in a book. If you don't know what the names are, you're starting from ground zero. Okay? And sometimes this is surprisingly subtle. That's why I'm going through these things kind of carefully. Any other questions about friendship or problems related to it? Okay? Very good. Okay. A second issue, now that we know how to model problems in terms of graphs, or now that we know to think in terms of graphs for our problems, we may want to know from an algorithmic point of view, how do we represent the graph in the computer? This is something a lot of you are wrestling with now in your programming assignment. Because you've got a graph you're taking as input, okay, and you want to store it in the computer somehow. There's several different data structures you can use, okay, but there's really 2 basic ideas that are mostly the ones that turn out to be useful, okay, and they are adjacency lists and adjacency matrices, okay. What are the differences? Well, one way we could represent a graph is by an adjacency matrix. Suppose this is our graph. Our graph here has 5 vertices, okay, and a bunch of edges. There's an edge from 1 to 2, but no edge from 1 to 4. One thing we can do is model this by a matrix, where we have rows and columns of the matrix, okay, such that the ijth element is going to be 1 if and only if there is an edge I to j. So, for example, there is an edge from 1 to 2. Sure enough, there's a 1 there. There is an edge from 1 to 5. There is a 1 there. There is an edge from 2 to 3. And 2 to 4 and 5. These are the 1s. Okay? There are no self loops. So everything along the main diagonal was a 0. Okay? No longer it's a 0. Now it's covered up. Okay? So in an adjacency matrix, we start out with an n by n matrix, and we can, look up in constant time whether or not an edge is there. You just specify, is there an edge between vertex I and j? Well, look at the ijth element and set it to be 0. See if it's 0 or 1. Okay? In constant time, you can check the presence of such a thing. Okay? Any questions? What is going to be true about an undirected graph, okay, that we represent in an adjacency matrix? Okay?
Symmetric to the main diagonal.
It's symmetric to the main diagonal. Why is that? This cell, remember, is 1, 5. 5, 1. If we reflect along the diagonal, the opposite one we get here is 1, 5. Okay? If I am your friend, you are my friend. Okay? So if this is 1, that's going to be 1. If this is 0, that's going to be 0. Okay? So in fact, in an undirected graph, it's symmetric. And so we could, in fact, if it's an undirected graph, we could throw out half the space, if we were really space conscious, okay, and simply keep the stuff up here. And then if you ask, is 5, 4 an edge, you simply reverse the question and say, is 4, 5 an edge? Okay? So if you really want to save space, you could conceivably do it if the graph is undirected by a factor of 2. Can you save memory if the graph does not have many edges in it? Okay? Here we take how much space to store a matrix on n vertices. Okay? N squared, an n by n matrix. How much space do we use if we have one edge in that graph? Well, if we use an adjacency matrix, n squared. We've got to set a lot of things equal to 0. If we have n squared edges in the graph, how much space does it take? N squared. The adjacency matrix does not, the space is not a function of how many edges you have. So if you have a sparse graph with very few edges, okay, like what I fear the friendship graph is, if you take a look at the world side, everybody has, there's 5 billion people in the world. Nobody knows more than 100 or 1,000 of them. Okay? If you wanted to represent the friendship graph, you'd need a billion by 1 billion matrix. Okay? And unfortunately, most of those entries are going to be 0. Okay? So that would be potentially wasteful, which is why we might need another adjacent structure called an adjacency list. Any questions about adjacency matrices? Okay? An adjacency list is a data structure that is designed to store graphs such that the space that it takes is a function of the number of edges in the graph. Okay? So if we think about representing the friendship graph of the world, it's a sparse graph. No vertex is going to have more than 100 more than a few hundred edges incident upon it. Okay? In an adjacency list, to represent graphs more sparsely, what we do is we represent the structure, we represent the matrix by by an array of n linked lists, okay, or an n by 1 matrix, where the ith element, okay, of our linked list, the ith element of our array is going to point to a linked list of all the edges incident upon that vertex. So for example, what do we know up here? Let's take a look at this graph again. Vertex 1 is adjacent to 2 and 5. If we take a look at the adjacency representation, we'll see that it's adjacent to 2 and 5. Okay? What is vertex 2? Vertex 2 is adjacent to vertex 1, 5, 4, 3. In fact, vertex 2 is adjacent to everybody. So sure enough, vertex 2 is a linked list, contains 2, 5, 3, and 4. The order of that linked list doesn't matter. Okay? Because if you think about it, the order of these edges doesn't have any meaning. Okay? I mean, unless you sort of assign something to the drawing. If we talk about the friendship graph, okay, what order should your friends appear around you in representation? It doesn't really make any sense. Okay, you may look, when you think about a road network, it's drawn on the plane, maybe there's a clockwise or counterclockwise ordering. Here. Okay, here I'm assuming the graph is undirected. Okay, if it's undirected, what do we know? If there's an edge from 1 to 2, that means there's an edge from 2 to 1. So let's look at this thing. Sure enough, there's an edge from 1 to 2 and an edge from 2 to 1. So in this representation, I'm going to represent for each vertex, I'm going to represent the list of things that it points to. Okay? So if the graph was directed and not undirected, I would simply have to delete one of these copies. Okay? Suppose, let's say that this was a directed graph. Namely, that this edge goes from 1 to 2, and maybe this edge is, there's 2 copies of the edge here, and this one only goes like that. There's an edge from 1 to 2, but there's no link from 2 to 1. So this cell wouldn't be here. Okay? And there's no link from 5 to 2. So this thing wouldn't be here. Okay? So an adjacency list can represent either directed or undirected graphs. Okay? And, okay, it's a nice, neat arrangement. Space-wise, this total space that it's going to take is how much? It's going to take one cell for each vertex. Okay? So it's clearly going to be order n space for this thing. How many memory cells do we need if we have m edges in an undirected graph? 2m. Okay? And so in this case, what we've got is order n plus m space. Okay? So how much space does it take if you have an empty graph? Okay, where there's no edges in the graph? And you still have to store the vertices. How much does it take if you have a complete graph where everybody is everybody else's friend? Okay? 2n squared or 2n squared plus n. Depending on what, how you want to talk about it. There's the n here, and for every one of these, there's going to be adjacent to n other things. Okay? Well, actually, in reality, it's sort of, you have to be careful. In fact, it's going to be n squared space, not 2n squared, because for each one of these, it's going to be pointing to one. There's going to be, for each vertex, is going to point to each of the n minus 1 other things. Okay? The truth is, in an undirected graph, if you have n things in a complete undirected graph, you have n squared over 2 edges. Okay, so that's the difference. Okay? In fact, for if you think about it in an undirected graph, you've got actually n choose 2 edges. Okay? Which is really n squared, n plus 1 times n over 2, I believe. Okay? And if you make it undirected, I think this becomes a minus 1 or something like that. Okay? But it's order n squared, and that's all that I deal with. Any other questions? Okay. Suppose I give you an adjacency list. Okay? How much time does it take to test if edge ij is in the graph? How would you test if edge ij is in the graph? Okay? You would look in the ith element of the array over here. Let's go back here. In constant time, you can find the ith linked list. This list contains all the elements that are a distance of that are from element I. Okay. Now you want to find whether ij is in the list. You cruise through this list and see whether or not there's a record labeled j. Okay. How much time does that take? Okay. It takes time proportional to the length of this list. If you wanted to ask whether or not, Scott Perlman is a friend of mine, okay, I don't know how many people here know that, okay, presumably no one knows that, okay, okay, what you would do is you'd have to go through all my friends saying, are you Scott Perlman, are you Scott Perlman, are you Scott Perlman, okay, so the time that it would take is proportional to the degree of that vertex, okay, because the degree of that vertex is exactly the length of that list. So in a sparse graph, a low-degree vertex, that becomes a fast operation. In a dense graph, it becomes a slow operation to look for an edge. Okay? Any questions about that? That should be believable. The other thing to see is that we can add other pointers and things to our... this is just the basic adjacency list representation. There's lots of different things you can do depending upon how clever you are or what you want to do. Like, for example, should this linked list be singly connected or should be singly linked or doubly linked. Okay? A lot depends upon what kind of operations you're going to be doing. If all you're going to be doing is searching in the graph, then it doesn't really matter. If you're going to be deleting vertices, edges from the graph, it does matter. Because once you find a particular edge here, if you want to delete it, you need to have the predecessor. Okay, so maybe it does or does not, okay, depending upon how you want to do things. Another pointer you might want to add to graphs, okay, is since there's two copies in an undirected graph, if there's two copies of a particular edge, like here we've got 3, 2, and here we've got 2, 3, you might want to maintain a pointer between them. So if you delete one copy of the edge, you know where to go to delete the other copy. So there's lots of extra flexibility you might want to add in building really good graph implementation. Okay, but the basic idea is as we've talked about. That's the idea of an adjacency list. Any questions about that? Okay.
Doesn't really have to be a list, right? If
What do you mean?
every vertex has a unique ID, I could also do anything which can be sorted.
Okay, so well, let's just think about it.
I mean, I could have a binary tree.
You could have any dictionary data structure hanging off of all to represent all the vertices. But I've never heard of a case where it's been useful to do something other than a list. Okay? Usually it's the case that with graph algorithms, you want to use a simple linked list is good enough, rather than representing it as a binary tree or a hash table or fancier things. Okay? Sometimes when you really want to save space, people will represent it by a small array. Okay, let's say you know there's only going to be 3 vertices on every vertex. You might want to use an array to represent that list instead of the linked list to save the space that you use the pointers. Okay, link the cells together. Okay, but basically you keep it simple. Okay, and this is basically the right way to do it. Okay, any other questions? So which is better, which is better, an adjacency list or an adjacency matrix? How many people think adjacency lists are better? Okay. How many people think adjacency matrices are better? Okay, a few people. The truth is, depends upon what you want to do. Okay? Which is better, a car or a plane? Okay? Depends where you want to go. Okay? Likewise, there's different advantages to adjacency lists and adjacency matrices, depending upon your particular application. So let's go through the list of possibilities and decide who the winner of each one of these comparisons is. Actually, maybe we'll try to cover this up so it looks a little prettier. Okay? So for which one, an adjacency list or adjacency matrix, is it faster to test if a particular edge is in the graph? Okay? How many people think it's faster on a matrix? Okay? How many people think it's faster on a list? Okay? Faster on a matrix. It takes constant time to change the bit in the matrix. Okay, to look for a bit in a matrix. You might have to scan through a whole list, okay, if you want to try to find that. Which one is it easier to find the degree of a vertex? Okay, I now have a vertex. I want to tell you how many friends does Saddam Hussein have? Okay, which is that faster to do on a list or a vertex? How many people say list? Okay, how many people say matrix? Okay, most people say lists, and lists are the answer. Why is that? Well, let's think about the case. Here's Saddam Hussein, okay? In an adjacency list representation, his list of friends is going to be given there. To count how many friends there are, we simply have to go through the end of the list, okay? Look at each element of the list, saying 1, 2, we at the end he had 2 friends, okay? In an adjacency list, the time that it'll take is going to be proportional to the number of friends. Whereas in an adjacency matrix, there could be 2 friends in a long list. Okay? And so in order to count that, we have to scan through all the people. Okay? And count how many ones there are. Okay? So it's faster to find the degree of the vertex in a list than a matrix. Any questions about that? Yeah.
Well, what if you added on a position and you kept the degree in the array?
One other possibility is, let's say, associated with each vertex, vertex in the matrix. You couldn't say with each matrix. You could have your adjacency matrix and also store a supplementary field, which is for vertex I. You tell how many edges there are in that. Okay? You could do that, okay? But, and maybe it's useful. But the point here is it's actually, the important thing is to see with an adjacency matrix, you can't get access to these edges, to see what those edges are without cruising over the zeros. Okay? That's the loss of flexibility you get. Okay? And while you may be able to kludge it up in this case, most of the time you can't. Yes?
What I was thinking of is if we have multiple edges in the order of like really huge numbers, if you have a linked list.
Okay. If we had multiple edges in a linked list, let's say that Saddam is not only has one friend, but he has that friend lots of different times. You're saying that that could be in a linked list in a lot of different records. Okay? How would you represent a multigraph using an adjacency matrix? Okay? How do you represent for ij that there are lots of different, all the different edges, if there's multiple edges between I and j? Okay? Well, you might say, well, keep count of how many edges there are. But that only works if all the edges are the same. Think back to that electronic circuit we showed. One of the edges was a capacitor, one of the edges was a resistor. Those edges were not the same. So how would you represent an adjacency matrix if you had multiple edges? Okay?
Store a pointer at that location to a list of.
Basically, one way to do it is you could store a linked list of all the edges. Okay? Adjacency matrices are not really designed to deal with multigraphs in a clean way. Okay? But we could represent it by each cell here being a pointer to a list of edges and store things that way. Okay? Any questions about that? Okay? Okay, we're getting a... Which graph, which representation uses less memory on a small graph, or on basically a sparse graph with few edges? Okay? How many people think lists use less memory on a small graph, a sparse graph? How many think matrices use less memory on a sparse graph? Okay? Well, by sparse graph, by small I meant sparse. Okay? If you have a graph where you've got very few, each vertex has only one vertex that it's adjacent to. Remember that's sort of a adjacency list. The space that we use is order m plus n, edges plus vertices. For an adjacency matrix, we always use n squared space. So if we have a linear number of edges, this is n squared. This is much less. If we have a quadratic amount of space, okay, now we've got a big graph. Which is going to use less space? An adjacency matrix or an adjacency list? How many people think an adjacency list will use less space on a big graph? Okay. How many people think adjacency matrices will use less space on a big graph? Okay, most people. The answer is an adjacency matrix will use a little bit less space. Why is that? Because in a complete graph, if we're representing it by an adjacency list, you've got n lists, each of which has n cells. It's going to take n squared space. So in a big O sense, both of them take n squared space. The truth is here, each element is more than one bit, yes or no. Okay? There's a pointer associated with it and a number associated with it. So if you have a really dense graph, okay, it's going to take a little bit more space on an adjacency list than an adjacency matrix because there's much more overhead, much more baggage. Okay? In practice, that's not usually a big problem, but if you have a huge graph that's going to be very dense, it probably pays to pack it in as a matrix. Okay? Any questions? Okay? What if you want to insert or delete an edge into a graph? Which is it faster to insert or delete an edge? Let's say we want to insert an edge into a graph. How much time does it take to insert an edge into an adjacency matrix? Okay? Constant time. All you do is you look up that bit and you change that bit. How much time does it take to insert an edge into an adjacency list? Well, it depends a little bit upon what you want to do. Okay? If you just want to insert it and you don't care if it was already there, it's just a question of inserting it at the start of the list. If you want to make sure there's not extra copies floating around, you've got to scan through that list to make sure it's not there. So that might be degree n. What if you want to delete a vertex from an edge from a graph? Okay? How much time does it take to delete something from an adjacency matrix? Constant time. Flip the bit. How much time does it take to delete something from an adjacency list? Linear in the degree of that vertex. Because you cruise down that list till you find it. You might be unlucky and it's sitting at the end. Okay? So adjacency matrices win when it comes to edge insertion or edge deletion. Which is it faster to visit all the edges of the graph? Okay? Let's say that you want to, let's say you wanted to count the number of edges in the graph. Okay? Or print out every edge in the graph. Which is it going to take more time to do? Okay, to print out all the edges if we use an adjacency matrix or an adjacency list. Okay? How many people think it's going to be faster with a list? How many people think it's going to be faster with a matrix? Okay, most people agree. Faster with a list. Why is that? Because we only have the edges in the lists. Okay? So in order m time, we could cruise every element of our linked list. Whereas if we have an adjacency matrix, we've got to look at every cell to see whether it's 0 or 1, which means that it'll take n squared time, just simply to find all the edges, even if the graph has very few edges. Okay, any questions? Okay. Which is better for most problems? Okay, I think I gave the hint away. Okay. My sense is it depends what you want to do. Sometimes matrices are a good thing, sometimes lists are a good thing. Usually, lists, I think, are faster in practice. Okay? Because most of the time we're dealing with fairly sparse graphs. Okay? Not always, but most of the time. And when we deal with a sparse graph, okay, usually there's a lot of algorithms that can run faster if we have them in adjacency list form. Most of the time this semester we're going to deal with things in adjacency lists. Okay? So let's think about the graph problem that you guys have, the bandwidth problem. Okay? What is the cost of doing it in an adjacency list versus an adjacency matrix? Okay? Both of them will work, and the data structure is not likely to be the bottleneck when it comes to sort of why your program is going to be very slow or very fast. Okay? Because you've got this combinatorial search, that's the bigger win. But if you think about it, if it's represented, what are you going to be wanting to do? What's the main operation you're doing in the loop of your bandwidth problem? Okay? Yeah? Testing for each edge in the graph, what's its actual bandwidth? How long is it in the current permutation? Right? Most of you will be arranging this thing. You've got some you'll try all permutations. And now you want to know for a given permutation, what's the length, the longest edge span given that permutation. What you really want to be able to do is, for each edge, say how long is it going to be. So the basic operation you're going to be wanting to do is cruising through each edge. Okay, and saying, well, how long is this edge now, given that permutation? Okay? And so you're better off with an adjacency list, probably, than an adjacency matrix. Okay? If you use an adjacency matrix, you're afraid of the pointers, don't worry about it. Okay? Stick with your matrices. Okay? But if I'm programming it, I use an adjacency list for this. Any questions? Yeah?
Don't we just use a list of edges?
Or something simpler in this case, just a list of edges. Okay? Any questions? Okay. That said, I'm now ready to answer the homework problem of the day. Okay? Which I guess was a little bit behind. Okay? But let's take a look at this thing. The homework problem of the day said the square of a directed graph, okay, VE, is the square, the graph G squared, which is the same set of vertices and a different set of edges, such that there is an edge, U, W, in the square graph. If and only if, for some vertex V, both EV and VW are in the edges of the graph. Okay? What does that mean? That means that there is a path of exactly length 2. So if in the original graph I have this vertex U and this vertex W, there will be an edge between, maybe there's an edge of length 1 between them in the original graph. If I now consider the square graph, okay, there will be an edge between here, if and only if there is some intermediate vertex, okay, such that there is an edge from here to here and an edge from here to here. When we ask in this problem, it says, give an efficient algorithm for both adjacency matrices and adjacency lists to construct the square graph. Okay? So let's just construct an example to make sure we understand it. That's how I do things. Okay? Here I've got a graph. Okay, let's say it's a directed graph. What is the square of this graph going to look like? Okay?
1 to 3 and 2 to 4.
Okay, we had a number of these things, 1, 2, 3, 4. The square graph, we will have a vertex, an edge like that, and an edge like that, and nothing else. Okay? What if we have a graph that looks like this? Where we have a star with, let's say, both edges directed both ways in the star. Okay, so for every edge here is one that goes there and one that goes back. What's the square of this graph going to look like? Okay, what's the square of this edge? Or maybe it's not drawn clearly enough. I have an edge like that, and 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 an edge like that, edge like that, and edge like that. What's the square of this going to look like? It's going to look like a complete graph. Is there an edge from here to here? Is there a path of... Oh, it's actually not going to be quite a complete graph. Okay? Because we want an edge of exactly 2. Between any of these outer vertices, all these outer vertices are going to be connected to every other vertex. There's a path from here to here, okay, of length 2. Because I can go from here to there, from here to there. What's going to happen to the center vertex? What is a distance 2 from the center vertex? Just himself. So we end up with the happy universe and the happy friendship graph and a hermit when we square it. Okay? Any questions about that? Okay? So that's what we mean by the square graph. How do we find the square of a graph? Okay? 2 different algorithms based on the data structures. Suppose the basic data structure is a adjacency matrix. What can we do? The way I would think about it is, we want to know in constant time, okay, whether that particular edge, we can check if we have an adjacency matrix, whether any given edge exists in constant time. Thus, if we want to discover whether there is a particular edge, okay, UV in the square graph for a particular pair of vertices U and W, that means we want to check all possible intermediate vertices V to see if there is an edge from there to there and back. So if we have an adjacency matrix, for any V from 1 to n, we can in constant time check to see whether UV is an edge and VW is an edge. There are n squared pairs of vertices. For each pair of vertices, how much time does it take to check if there's an intermediate vertex? Okay? For any one intermediate vertex, it means looking up 2 cells in the adjacency matrix. If we want to check if there is an intermediate vertex, we've got to try all possible vertices as intermediates. Okay? There are n possible intermediate candidates, n operations, each of which takes constant time. Okay, it means it takes linear time to check for a particular pair, n squared pair. The total time is n cubed. Okay? How many people understand where that came from? Okay, how many people do not understand where that came from? Okay? Let's ask again. How many people understood where that came from? How many people did not understand where that came from? Okay, a majority. Okay, what's the idea here? How do I tell whether there's a path of length 2 from I to j? If there's a path of length 2 from I to j, what do I need? I need an intermediary point. Okay, and not just a point, but I need it to be that there's an edge like that and an edge like that, right? If I have a graph of n vertices, how many possible intermediary points are there to look at? If I have n vertices in my graph, maybe some of them don't quite get it. Maybe some go the other way. Okay? How many vertices might I have to look at to find an intermediary? n minus 2 or order n. If I have an adjacency matrix, how much time does it take to check for a particular element here? Does this edge exist? Constant time. So I've got n operations, each of which involves looking at 2 cells in the array. That means it's going to take linear time for a particular I and j to see if they're connected. How many I and j are there? Okay. There's n squared pairs. Each pair takes n to compute. N squared times n is n cubed. That's n cubed time. Okay? Any questions about that? For adjacency lists, how much time does it take to find things? Okay? How could we go through and decide? There's a couple different ways you could do it. The way that I would be doing this, okay, is a little bit tricky. If I have an adjacency list, I have a list of all the edges in a graph. Suppose I've got some edge, uv. What edges in the square graph might possibly depend upon this? Okay? Or how might I use this edge that goes from u to v? Okay? I can use it to create any edge that goes, if there's any edge from v to someplace else. Given this particular edge, if I have one other edge from v to someplace else, that means there's going to be an edge from here to here in the square graph, correct? How much time will it take for any particular edge to check all the edges that might be created, okay, by using that edge in the square graph? Okay, what do I have to do? Okay, to find out all the edges that might be created using this edge. Okay? I want to know all the vertices, edges that are adjacent to v. For any edge that's adjacent to v, I am creating, if this goes to x, that means that I have an edge in the square graph from u to x. Maybe I'll create it lots of times, but certainly I can, let's say, identify my duplicates if I do it in the right way. My claim is I could do it as follows. If I take my adjacency list, for any given edge, okay, I'm going to run through all the edges, any given edge uv. I'm going to take a look at all the edges that go from v to somebody else. Okay? How many edges might leave v? At most n of them. Because every edge is leaves v is defined by v in some other point. Okay? So my claim is that in order n time, given an adjacency list, okay, I could find all the edges created using that edge uv. I could, if you want, build an adjacency matrix for g squared. Initially it'll be empty. Whenever I create an edge, I'll fill it in. It'll take constant time to fill it in. And if I've already filled in one copy of the edge, let's say when there's more than one path between two vertices, I can ignore it the second time. Okay, and look to see if it's there. If it's there, I'm not going to change it. So how much time does this take? For each edge in the graph, okay, it's going to take n time to find out its consequences. How many edges are there in the graph? m edges to start with. For each edge, there are n consequences. Okay? That said, the total time it's going to take is n squared times m. Okay? I mean, there's a little bit of bookkeeping I don't want to confuse people with. Okay? So this algorithm is going to be n squared times m. Okay? Is this algorithm better than the n squared algorithm? N cubed algorithm? How many people think it's better? Okay? How many people think it's worse? How many think they can't really tell? Okay, a lot of people can't tell. How many edges might the graph have if the graph is sparse? Okay?
0.
Might have 0 or, well, if it's 0, then it's, okay, it's very sparse. In a reasonable case, it may have n edges, typically. I mean, graphs with 0 edges usually aren't that interesting. But graphs with n edges or 2n edges often are very interesting. Okay? So it's not, it could be that m is order n. If it is, then what is that mn algorithm? N squared. That's much better than n cubed. What happens if the graph is very dense? Okay, what's the maximum number of edges the graph can have? N squared. What would the mn algorithm be? Then that would be n cubed. So if the graph is dense, the two algorithms run the same. If it's sparse, the adjacency matrix wins. Okay? And that's true in life, okay, in most cases. Any questions? The adjacency lists would be better for sparse graphs. Okay? Final question, why do they call this the square of the graph? Turns out, if you think about it, if you take the adjacency matrix of the graph and square it, okay, take that matrix and multiply it by itself, the amazing thing is that you end up with the adjacency matrix of the square. Okay? If you want to go and convince yourself of that, you can play around with it. Okay? But the more important thing is to see why these two situations are different and see where they both come from. Any questions? Okay, that said, we'll continue with graph algorithms next class. Okay, good luck. Sign up for pizza and see you guys and see your programs next class. Thank you.